All right, we are now looking at 9.2, Mastery Learning Objective, and this is kind of the new part of exponential equations. We're now going to look at what we call logarithms. And a logarithm comes in with this idea of everything in math has an inverse or an opposite, right? So when we're solving equations, or if we're solving something like x plus 3, we subtract 3 because addition and subtraction are opposites. We've seen multiplication and division, right? We're used to squaring something and then square rooting something, right? So all of these things have opposites. So we need an opposite for when you have a variable in the exponent. And so the opposite of an exponential equation is what we call this logarithm. Okay, so that's really how we're going to define it. So a logarithm is the inverse, right? That's the math word for opposites. Right, so addition and subtraction are technically inverses. The inverse of exponents. I can't spell. Put another E in there. Okay. And now we write a logarithm is we have log, which is, I would say, normal size. And then we say base B, that's little, it's a subscript of x, normal size, equals y. Okay? And we write this as log, or we say it as log base B of x is y. And this is the opposite, or the inverse of exponents, because this is the same as saying b to the y equals x. Okay? These two things are the same, just in different forms. And he's saying like 5 plus 3 equals 2, and 5 plus 3 equals 8, and 8 minus 3 equals 5, right? Those are kind of using the same numbers. It's kind of the same idea. One's just addition, one's subtraction. Okay, so that idea of like a family of numbers still holds when we're talking about exponents. Okay. There's two weird logarithms that we look at. One is called the common logarithm. That is a logarithm with base 10. We call it the common logarithm because a lot of things in our world use base 10, right? Because our counting system is in base 10. And so therefore, if I ever have log base 10 of something, we'll just sit with x equals y. Log base 10 of x equals y. We really just write it as log of x. Okay? So when there's no base, the base is 10. We also have the natural logarithm. That's a logarithm with base equal to e. E is your natural number. This might be new to you, but it pops up a lot. Like pi, it's a constant. 2.71 blah 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 blah. It's another number that goes on forever. Okay, so e is just a number. It's called a natural number. It pops up a lot in nature. How plants grow, how weird things happen. All have to do with e. Someone discovered it. So if I was to write a log base e of x equals y. And how we write that is we write the natural log. I call it the natural log, or we write ln. It's out of order because the first person to develop the natural logarithm was French. So just like Spanish or all those other, it's logarithmic natural or whatever it is. So we put the other one first. So that's why it's ln and not nl. But we say natural log because we speak English. Right? To be natural log of x equals y. So a few weird logarithms that we might encounter there. Alright, so let's look at an example. Okay. So here we have things that are in logarithmic form, and I want to write them in exponential form. The easiest way I know to do it is what I call the loop method. You start at the base, and you loop around. Okay. So with my base, it's 2 to the 4th equals 16. Okay. So what's over here becomes your exponent. And this ending part becomes your answer. Same thing here, right? We're going to loop around. 4 to the 0 equals 1. When you're first starting, right, you could pull up a calculator and see if you're right. 4 to the 0 equals 1. Got it. Okay? Same thing here. 12 to the 1 equals 12. D is a little odd, right, because there's no log. So again, we put a 10 down here. When there's no number, it's the common log. And then we still just loop around. 10 squared equals 100. I'm going to do one other problem. If I had like the natural log of 5 equals 1.6. Again, this is the natural log. That just means it has a base of e. So if I'm switching it, I like to put that so that I can still just do the loop around. So that's e to the 1.6 equals 5. That's really all it is for that rewriting, switching them. If we look at example 2, right, now we're going the other way. Right, we have an exponential form, and we want to get into logarithmic form. The same method still works. Loop around. We start with our base. So log base 5, right, by looping around, 25 comes next, equals 2. Okay, so log base 5 of 25 equals 2. So your first, like, there's always two numbers before your equals sign. That could be another good way to think about it. Same thing here. Log base 10 of 1/10 equals -1. Here, however, I'm then going to switch that to just be log of 1/10 equals -1, right? That's our common logarithm. We don't write the base. Looking at C, log base 8 of 4 equals 2/3. So even if it's a fraction here or like a fraction here, right, it still works. Letter D, log base 6 of 1 over 216 equals -3. Let's do a one with E. Oh, and it is letter E. So if I have like E to the 7th, well, 1097, right? Can loop around. So it's log base E of 1097 equals 7. And I'm just going to rewrite that as really the natural log of 1097 equals 7. Okay, so again, that's just a standard notation part of that. All right, go ahead, turn to the next page. Why do we care, right? Why, or why do we switch them, right? It's very hard to think in logs, so we'll usually switch them to exponential forms if we're solving or evaluating the log. Also switching from exponents to logs helps us solve equations, which we'll notice later on. But right now we're going to look at evaluating these. So I want to know what this is going to be equal to. So for right now I'm just going to set it equal to x. I'm going to loop around. I'm going to switch it. 4 to the x equals 64. Alright, so if I'm trying to evaluate it without a calculator, now that it's an exponential form, I can think about it easier. Right, 4 multiplied how many times is going to give me 64. So it's 4 times 4 is 16 times 4 is 64. So that means x equals 3. Right. Same thing here. If I'm evaluating this, 5 to the x equals 1/5. Remember, if you want to get your base on the bottom, a negative exponent flips the fraction. So this is in the opposite, if it's a numerator or denominator, it's in the opposite one. So x is definitely going to be negative. And 5 to the first, 5 to the 1 equals 5. So we get x equals negative 1. Looking at letter C, log base 1/5 of 25. Right, again, we're evaluating this. So it's 1/5 to the x equals 25. Same thing with the negatives, right? This is in the denominator, we're switching it out of the denominator. So x is going to be negative, and then 5 squared is 25. Last one. 36 to the x equals 6. Well, 6, right, if I'm going down, so like, this isn't raised to this power, this one's raised to this power, right, the easiest way I think to remember is that, right, the square root of 36 is what equals 6, and this is the same as saying 36 to the 1/2. Okay. So kind of starting to introduce that idea of remembering that a square root is also a fraction exponent. And that's actually going to come in later on in this unit again, so it's a good thing to start remembering about that. Alright, that's it, and I will see you guys on Monday.